Hello, my name is Sergio Soto. I am currently pursuing a Master of Science in Applied Statistics and Data Science at the University of Texas at Rio Grande Valley, and I'm going to present to you quantization for the mixtures of overlap probability distributions as part of my master project presentation. A brief overview on what I want to present today. I'm going to start with some definitions of what is quantization, what are the goals and challenges, what are some applications, and the motivation for my research. And then I'm going to go over the four sections of my research paper. In the introduction, I'm going to give a big picture and rigorous math definitions. And then in section two, basic preliminaries, I'm going to start explaining more about these um, definitions from the first section, and then talk about the mixed distribution for a certain case, and then give you how the algorithm, or I'm gonna actually explain to you the algorithm that I was able to find in my research. Um, so, what is quantization? It is the division of a quantity into a discrete number of small parts. And the oldest example is rounding off, which was first analyzed in 1898 by Shepard for the application of estimating densities by histograms. Then the research increased in the late 1940s, and its importance was recognized in analog to digital conversion systems. So, how or where is quantization in that process of converting analog signals into digital signals? So, whenever you have an analog signal, it passes through a system that wants to sample the analog signal into discrete um, bits of information, and then they want to process it to remove some of the noise. And depending on the application, you want to get that analog signal back, but without the noise or without the or yeah, pretty much filter out. So in quantization, what we want is to preserve as much as information as possible from the analog signal, from the original analog signal. And by the less amount of bits, we want to recreate that signal. So we want to preserve as much information without losing uh, important pieces, right? So the goal is to encode data from a source characterized by its probability density function into few bits as possible with low rate, in a way that a reproduction may be recovered from the bits with a high quality as possible, with small average distortion. As you can see in these pictures, um, we are trying to represent with these rectangles the area under the curve of this sinusoidal signal. But you can see that with less rectangles, we have a larger distortion compared to this one. Whenever you have smaller bits, smaller size in the delta, in this case, let's call it delta t, and we have more bits to represent the area under the curve, we preserve more information. So with higher sample rate, we have less distortion, and this is the trade-off that we want to achieve. We want to achieve the least amount uh, of rate as possible, of bits as possible, that will yield the least average distortion. And one of the questions that we face is, well, how do we find or design these optimal quantizers? And some applications that that we have for quantization are in the field of communications and signal processing, what I mentioned in analog to digital conversions, also in data compression. There's also application in statistical clustering, like whenever we're grouping bird songs or grouping gene features or classifying the classification of organisms in taxonomy. Also, it's important in placing points in space, like, for example, finding the optimal location of where to place mailboxes in an apartment complex or some wireless sensors, um, I don't know, in a building or telecommunication towers away from a city. Also, in image and video classification or segmentation, in speech recognition and speaker identification, and in numerical integration and optimal quadrature rules. Now, the motivation of my research. In my research, I'm going to study quantization in the mixture of overlap probabilities because there is little to no research in that field or considering the mixture of overlap probability distributions. And the goal is to advance existing knowledge and theories on quantization. And why not, like, model some real world scenarios? Um, like when I was studying um, mixed probability distributions, I was thinking on what kind of applications was this useful for. And um, I was thinking on maybe this case where we want to consider the optimal location of placing wireless towers away from cities. So we know that like if we place these towers closer to the city, well, that's more beneficial to the users. It's more important to have them placed closer to the city than away from the city in rural areas. So I'm going to explain more about this situation in the next slides. So pretty much is having points closer to like a center, and the distance it's growing apart as we move away from that center. And that is because the probability of finding these optimal locations of the tower in these mixed probability distributions are closer to the city. Let's start with part one of the research paper, the introduction, and it's going to be some rigorous definitions in math, but bear with me, I'm going to explain later on all of this. So let's start with RD being the d-dimensional Euclidean space equipped with a metric compatible with the Euclidean topology. And let P sub 1 and P sub 2 be two Borel probability measures on RD. Then a probability measure P on RD is called a mixture or a mixed distribution generated by P1 and P2 associated with a probability vector P comma and 1 minus P if P is defined as uh, little p times P sub 1 plus 1 minus P times P sub 2, where P is between 0 and 1. Okay, so it's just the definition of how we are getting that mixture or mixed distribution generated by these other two Borel probability measures. And then we're going to define a way to quantize um, the error. And this is going to be the end quantization error for P with respect to the square Euclidean distance will be defined by this. And it's going to be the infimum of this, uh, it's a conditional um, distortion error. And it's right here is defined as the minimum, the integral of the minimum of an this is a quantizer element of the optimal set, and I'm gonna define this in the next slide. And this is pretty much just uh, taking the square Euclidean distance and finding the minimum. And this is going to be the distortion error due to the set alpha with respect to the probability distribution P. So the end quantization error is just taking the minimum value of this distortion error, and alpha is a subset of RD, and the cardinality of alpha is between 1 and n. So as I promised you, I'm gonna here define the optimal set, which is a subset of RD. This is the optimal set of n means for P if the end quantization error equals to the distortion error. It is known that for a Borel probability measure P, if its support contains infinitely many elements, and this is finite, then an optimal set of n means always has exactly n elements. And the elements of an optimal set of n means are called optimal quantizers. So here you can imagine that if we have a set, suppose consisted of these gray circles, we can like define an optimal set of three means like this, where each element here, the purple circle, the green circle, and the red circle, it's called an optimal quantizer. And pretty much what they do is um, we can imagine this is like the centroid of this group right here. It's um, the Kane mean, whereas the distance between the gray circles is minimum to this. So this is like the best possible circle that it's in the center, so to speak, of this group of points, similar to this one right here. The the green circle, it's in the center of this, so the distance between each gray circle to the green circle is minimum, and the red one as well. Okay, now this is the case where R is in one dimension. And let's start with a proposition 1.1. Let alpha be an optimal set of n means for P, and A be an element of alpha. Then the probability of the Voronoi region is positive. That's one condition. Two, the probability of the boundary of the Voronoi region equals 0. And three, A equals to the conditional expectation of the random variable x, given that x it's an element of the Voronoi region. So here, this right here is the Voronoi region of A element of alpha. And the Voronoi region is the set of all elements x in Rd which are closest to A among all the elements in alpha. So what is a Voronoi region? Okay, so it's we can think of it like a closed space. And right here, you can observe, let's focus on this picture for two dimensions, for R2. So here we are representing the optimal sets, and each of these are the quantizers, okay? So this is one quantizer, another. And the set, in this case of uh, 5 means, consists of these orange 5 dots or points. Now, it is a closed space. Now, a Voronoi region will take, it's going to be like the continuous case where the space around this dot is closest. So right here, if you see this part, you see a boundary between this quantizer and this other quantizer. So the points in this region, like the space, like pick any point in this region, suppose here, where I'm placing my cursor. Well, the distance, well, we lost it here, but the distance between this point in space is closest to this quantizer. Okay, now what happens to the points in these boundaries? Well, we're going to define that to be that the probability of the points on that region is 0, but we don't know where, like, we don't know exactly if the points will be closest to this point right here or close to this right here. Okay, so we're just saying that at that point, the probability of having a quantizer that represents like that has its minimum value, either this one or this one, is 0. Okay, so here you can see how some regions emerge And every space, for example, in this region right here has a minimum distance to this quantizer right here. Now you can observe that a we can have it in 3D, the Born region in 3D and in 1D. And in fact, throughout my presentation, I will show you a lot of 1D visualizations of the Born region because our focus will happen, our research will happen on the one dimension. Okay, so this is how I am going to be representing uh, the Voronoi regions and the quantizers in that line segment. So in my research, I'm going to be considering the interval from 0 to 1.5, and I'm going to be using these orange stars as the optimal quantizers, and I'm going to be calling them just quantizers or points. And I am going to be representing boundary of Brunel regions as dotted lines like this. And here I'm representing some tick marks, okay? So this one right here is the intervals, or I mean the point 0. I'm going to be, again, talking about the interval 0 to 1.5, okay? So 0, 0.5, 1, and 1.5. And I'm marking here 3/4 because it's going to be important, and I will explain why this line is important in my research. All right, now let's explain more about the some of the rigorous math that we introduced in section 1. And let's start with defining f's of 1 and f's of 2 as the respective density functions for the uniform distributions piece of 1 and piece of 2. Remember, we uh, let piece of 1 and piece of 2 be two Borel. Um, it was probability measures, two Borel probability measures. And let's um, define define to be on the closed interval 0 to 1 and 1/2, comma 3/2. So we have these two independent Borel probability measures, and we have these two independent density functions. And f sub 1 is defined as is equal to 1 if x belongs to the interval 0 to 1 and 0 otherwise in this picture. And f sub 2 of x equals to 1 if x belongs to this interval 1/2, comma 3/2, or 0 otherwise. So we have these two independent probability density functions. Now, as we mentioned in section 1, let's consider the mixed distribution defined by this expression where p is between 0 and 1, and p has support. We can see that p has support the closed interval 0 to 3/2, and the component probability piece of 1 and piece of 2 have the overlap on the interval 1/2, comma 1. So let's now define the function f on the real line R such that f of x equals p if x belongs to the interval 0, close interval 0, comma 1/2, 1 if x belongs to the interval 1/2, comma 1, 1 minus p if x belongs to 1, comma 3/2, and 0 otherwise. So this is a picture of this probability density function with, in this case, I was just representing, well, what happens if little p is 0.2. Okay, so if p is 0.2, this is what f of x will be. It's going to be 1 in this interval always. And then 1 minus p, well, that will be 0.8, as you can observe here. Now, in this example, notice that f satisfies the following properties to be a density function, because f of x is positive for all x in R, and also the area under f of x equals 1. If you find the area under the lines, we get that the total is 1. So the mixed distribution P can be identified as a probability distribution on R with the density function f. That is, for any x in R, we have that the differential of P of x equals P times the differential of x equals to f of x dx. So now let's or talk about this lemma 2.1 that I found. If we let P be a probability distribution with a density function f and x be a random variable with distribution P, then its expectation and variance are respectively given by um, e of x equals 2 minus p divided by 2, and the variance of x equals to this expression right here. So let's prove this by a definition of a probability density function of x. Differential of f of p of x equals to f of x dx. And um, if we apply also the definition of the expected value of x, the random variable x, we have that is the integral of x times dp. And if we integrate over the the intervals, we integrate over the intervals we defined previously, from 0 to 1 half, from 1 half to 1, and from 1 to 3 halves with their corresponding probabilities, um, or f of x, we get this at the end, 2 minus p divided by 2. Similarly, by applying the definition of the variance of x for those intervals, we get the expression. Now, some important propositions for uniform distribution functions. 2.3 says, proposition 2.3, let P be a Borel probability measure on R such that P is uniformly distributed over a closed interval a comma b with a constant density function f such that f of x equals t for all x in the interval a comma b, where t belongs to R. Then the optimal set of n means and the corresponding quantization error of n means for the probability distribution are respectively given by this expression, and this is for the optimal set, this is for the quantization error. Now what this tells us is that for a uniform uniform probability function, we can easily find every quantizer. And this is because the probability is uniform, so we are expecting the quantizers to be equal, like equal distance apart from each other. If we consider like R1, which we are considering here in R1, so it's very straightforward. How can we find those quantizers and the variance as well for the whole set? Now, proposition 2.4 is very similar. However, here we are including an optimal point, a quantizer at the, here it says at the endpoint B. So let's suppose we want to include a quantizer at the endpoint B, and the the expression, like the formula to find every quantizer, will change a little bit, um, as well as the corresponding quantization there. Now, this will be important for when we study, or for whenever we study the mixed probability distribution functions, and some of these terms are going to appear there. So now let's talk about the optimal quantization for the mixed distribution P when little p equals 1 half. So what happens to the probability density function when little p is 1 half? So you can see that if we let p equals 1 half, we get this. It will reduce to this. F of x equals 1 half if x belongs to 0, comma 1 half, or 1, comma 3 halves. Or f of x equals to 1 if x belongs to this interval. It's in this interval, 1 half, comma 1. So you can see this picture right here, 0 otherwise. Now notice that the probability measure P is non-uniform and symmetric about the point 3/4. That means that if two intervals of equal lengths are equidistant from the point 3/4, then they have the same P measure. So it's symmetric about this point. That's why I was telling you that 3/4 it's going to be an important point in this study. Now, the probability underneath this part is equal to this part right here. It's very clear. Now, for p, little p equals 1 half, and using lemma 2.1, we can get that the expected value of x equals 3/4, and the variance of x equals 7 divided by 48. This is the quantization error. Okay, so by proposition 2.3, we get the optimal set for one mean of little p equals 1 half is 3/4, and the corresponding quantization error, as I explained, is 7 divided by 40. So not a very interesting example. It's just, well, what would be the best point, so to speak, if we want to place a 1 point in the interval 0 to 1.5 with these probability functions that we define. So not very interesting. The point will be in the middle. It will be at 3/4. But we will find later on uh, the means for 2, 3, 4, and 5, and 6. Now a remark 3.1. Since the probability distribution is symmetric about the point 3/4, without any loss of generality, we can always assume that if alpha of n is an optimal set of n means, then for a not positive integer n, the point 3/4 um, it's an element of the optimal set. And all other elements in alphas of n are equally distributed on both sides of 3/4. On the other hand, if n is an even positive integer, then all the elements in the optimal set will be equally distributed on both sides of 3/4. Thus, we see that n is even or odd. In any case, an optimal set alphas of n means contain equal number of points from both sides of the point 3/4. So this is basically saying that 3/4, because it's in the middle, as I showed here, uh, since it's in the middle, we can consider the quantizers, like we can find the quantizers in the left side of 3/4, and by symmetry, we can measure and calculate the quantizers um, that appear in the right side of this like line segment, right side of 3/4. Okay. Now, if we have an odd number of n's, like if n is odd, we are expecting to always see a quantizer at 3/4. Okay. And if we have an even n, then we're not going to have a quantizer at the middle at 3/4. However, we're going to have still that symmetry. That symmetry is going to appear no matter if n is even or odd. Okay. Now see, take a look at this. When n equals 3, then we have 1 point in this interval. This is from 0 to 0.5. And it's symmetric in the other side. When n equals 4, look how these quantizers are closer to the center compared to A1 and A4. Okay, so the points are closer. Imagine that picture. Think again about that picture that I showed you about the towers, the wireless towers. Think of this as the important uh, center of the city, where like you want the towers to be closer to this particular point for whatever reason. So you want these A2 and A3 to be closer. So this is what's going on in this case. So let me explain proposition 3.2. The optimal set of two means are these two numbers with quantization error given here. Let me show you the proof and show you some pictures so you can now uh, again think about this whenever I explaining uh, the optimal set for 4 or 5 means. Okay, so let's start with alpha being or like consist of A1 and A2, the two optimal set of two means, an optimal set of two means. Since the points in an optimal set are the conditional expectation in their own Voronoi region, we can assume that A1 is greater than 0 and A2 is greater than A1 and A2 is less than 3 halves. Due to symmetry of the probability distribution P about the 0.3 we can assume that the boundary, and this is important, the boundary of the Voronoi region of A1 and A2 passes through the midpoint 3/4 of the support of P. Okay, so we are in the case for two means. Okay, we don't expect to see a quantizer in 3/4. So we expect to have one quantizer in the left side and one in the right side of 3/4. Okay, so where along 0, comma 3/4 are we expecting to find A1? So where along this interval from 0 to 3/4 are we going to have A1? So we take the conditional expectation that of x such that x belongs to the interval 0 to 3/4 after applying the definitions here. We get, after doing some calculations, we get that it's at 7 divided by 16. And due to symmetry, A2 will be, well, 1.5 minus what we obtained for A1. And we found out that it was 17 divided by 16. Okay. So here's a picture. Now I'm representing here, maybe it's because it's overlapped, but here in this yellow dotted on top of the 3/4 marks represents the boundary region. Remember that first picture of Voronoi regions? So the point 3/4 is neither, like that point is the probability of that point equals 0. Like that point is not associated with this A1 nor with this A2. So for example, the point 0. This 0.5, let's suppose 0.1. Well, the point 0.1 will be closest to A1. So think of this like a tower, a wireless tower. If you have a point here or some user on this point right here at 0.1, well, it will be it will catch the signal from this tower, right? If it's here. What happens if a user is in this boundary region? So it could go either way. Okay. Now let's talk about proposition 3.2. I'll continue with the proposition 2.2 here. Again, due to symmetry, the quantization error for the two means is given by this. We're multiplying times 2 because we have to account for A1 and A2. Remember, we have one quantizer in the left side of 0 to 3/4 and another quantizer from 3/4 to 3/2. So we have to account for those two. So that's why we multiply times 2 and we get this value. Okay. Proposition 3.3, the optimal set of three means is this set with quantization error 1 divided by 48. Again, let me quickly go over the proof. Let alpha be an optimal set of three means. As mentioned in remark 3.1, we can assume that 3/4 is a quantizer, and let the other two elements in alpha be A1 and A2, such that A1 is greater than 0 and less than 3/4. A2 is greater than 3/4 and less than 3/2. Now, the boundary of the Voronoi region of A1 and 3/4 is given by this. It's A1 plus 3/4 divided by 2. Okay, so this is what we know so far. By remark 3.1, we expect to have a quantizer at the point 3/4. And due to symmetry, we expect to see one quantizer here between 0 and 3/4 and another quantizer between 3/4 and 1.5. So where along 0, 3/4 are we expecting to find A1? So if you think about it, if we find A1, because again, due to symmetry, we can calculate A2. Okay, so we are trying to find A1. If we find A1, we're done. We can find A2, and we have our three locations for our quantizers. So where are we expecting to find A1? Well, it depends. It will depend on where the boundary of the Born region lies. So remember, there's going to be a division between where the quantizer is between the A1 and A3 right here. So we don't know where that boundary will lie. So we expect to have two cases. So in case one, we're going to assume the boundary of the Born region is less than or equal to 1/2, like in this picture. The boundary of the Born region is less than 1/2. And in the other case, in case 2, we will assume that the boundary of the Born region is greater than or equal to 1/2. Okay? So in case 1, as I said, when the boundary of the Born region is less than or equal to 1/2, we can find the minimum distance for the distortion error, and we get this expression, and using um, mathematical software, we can find the minimum value, which occurs at when A1 equals 1/4. So we're getting an expression, and then we are finding the minimum value of that expression, that function. Okay. In case 2, if we consider that the boundary of the Born region is greater than 1/2, we again integrate, find the distortion error, integrate over the interval. We get the expression right here. It's different from case 1. However, when we find the minimum value, we get the exact same answer. So we found the local minimum of these two functions, and they happen to be at the same point. So we agree that A1 would be equal to 1/4. So we know A1 is at 1/4. Then what we can do is do 1.5 minus 1/4 to find the location of A2, which is 5/4. Okay. See again here, the boundary of the Born region will lie at 0.5. So it's the boundary of the Born region from between A1 and A3, and the other one is between A3 and A2. Okay. Similarly, we can calculate the optimal set for 4 means. Let's see here the picture and the boundary of the Born regions. The optimal set for 5 means. And then we found a lemma 3.6. Let alphas of n be an optimal set of n means for n greater than or equal to 4. Then alphas of n contains points from both the intervals 0, 1/2 and 1/2, 3/4. So starting n equals 4 and so on, and 5, 6, 7, 8, and so on, we are expecting to have quantizers, the points, the optimal points, in both intervals, from 0 to 1/2 and from 1/2 to 3/4. In proposition 3.7, we're given the optimal set of 6 means as follows. So here it is. And in summary, this is what we get. Okay. See how the closer we are to 3/4, the closer the distance is between the quantizers. Okay, the quantizers here are closer to each other in the middle. So let's recapitulate. From previous remarks and propositions, we found the optimal set and quantization error for n equals 1, 2, 3, 4, 5, and 6. We know that if n is odd, then the optimal set alphas of n means always contains the point 3/4. To find the quantizers of an optimal set, whether n is even or odd, it is enough to find the elements in the interval 0, 3/4, and the remaining of the elements in alphas of n can be obtained by taking the reflection with respect to the interval 0 to 3/4. Very important one. If we get all the quantizers from the interval 0 to 3/4, we can automatically, well, measuring, calculating, we can get the quantizers in the right side of 3/4. And an optimal set alphas of n for n greater than or equal to 5 contains quantizers from both open intervals, 0, 3 fourths and 1 half, 3 fourths. So, the question is, can we find an algorithm to calculate the optimal set for any n? And we are going to get there. I was able to find an algorithm for that, so let me explain. So we're going to start first by a lemma, by defining here given a lemma, sorry, 3.6. An optimal set alphas of n for n greater than or equal to 5 contains points from both the intervals 0, 1 half and 1 half, 3 fourths. Thus, there exist two positive integers, k and m, which both depend on n, such that um, alphas of n in the interval in the intersection with the interval 0, 1 half consist of these quantizers. So what this is pretty much saying is that when n is 5, 6, 7, 8, or 9, and so on, the quantizers in the interval 0, in the closed interval 0 to 1 half, will contain, we will be calling these quantizers from this interval, we'll be referring to them as A1, A2, A3, where A1 will be less than A2, A2 will be less than A3, and AK will be like the last quantizer in that interval. So look at the picture here for n equals 6. So this part right here means that A1 is right here, right? A2, it's greater than A1. Okay. But we don't have more quantizers in this interval. So in fact, AK will be A2. Okay, AK is the last quantizer in this interval. Okay, and right here, alphas of n, the intersection of the optimal set in the interval 1 half, 3 fourths, it's defined as the quantizers in that interval, and if n is even, we're going to have b1 less than b2 less than bm. But if n is odd, remember that if n is odd, we're going to have a quantizer at 3 fourths. So basically, this is just telling you, okay, consider now the quantizers in the interval 1 half to 3 fourths. Take a look here at n equals 6. From 0.5 to 3 fourths, we only have one quantizer. Okay, this in fact is b1. Okay, if n is odd, consider here n equals 5. Well, we have a quantizer at 3 fourths, and we have a b1. So b1 will be the first quantizer appearing in the interval 0.5 to 3 fourths. bm will be the last quantizer in the interval 0.5 to 3 fourths. Now, it's going to be very important, uh, the boundary of the Voronoi region between AK and V1. That will be very important in our study. Observe that in the above expression, if n is even, then 2 times k plus 1 equals n. And if n is odd, then 2 times k plus m plus 1 equals n. So remember, k now will be the number of quantizers. K will represent the number of quantizers in the interval 0 to 1 half. And m will represent the number of quantizers in the interval 1 half to 3 fourths. Now, we are not going to consider, well, if n is even, we don't have 3 fourths. If n is odd, we have 3 fourths. Um, Notice that in the following two cases can happen. Either the boundary of the Voronoi region between AK, remember, the last element in the interval 0 to 1 half, um, And B1, what I said, the first quantizer in the interval zero point 0.5 to 3/4 can be less than or equal to 1/2, or can be the other way, can be greater than or equal to 1/2. Whether, doesn't matter if n it's even or odd. And what we're going to be defining now is the n quantization error for the first case. So when the boundary of the Born region is less than or equal to 1/2, we're going to be calling that B1 of k comma m. That would be the quantization error for that case. And B2 of k and m will be the n quantization error for when the boundary of the Born region is greater than 1/2. So we're going to be comparing these two, and what we want is actually we want to find the lowest value. That means we're going to be finding the lowest distortion error, and that will be important for our algorithm that will find the optimal quant, quantizers, optimal sets. So now remember that we will be focusing on the interval 0, 3/4. Remember, if we focus on this line segment, the piece of interval, we can calculate the remaining quantizers due to symmetry. Then the following propositions will give the optimal set of n means and the n quantization error for all n greater than or equal to 6. Proposition 4.1, it's going to work for when we have two or more quantizers in the interval 0 to 0.5, and only one quantizer in the interval 0.5 to 3/4. Okay, we are just giving here the expressions on how to find every quantizer, how to find B1, depending again on where the boundary of the Born region lies. Okay, B1 in this case, because we have m equals 1, only one quantizer in 0.5 to 3/4. B1 is not going to change. Okay, um, but A1, A2 will definitely change. The quantization errors for n means are given below. Considering we have to consider the case when n is even, when n is odd, we have different expressions. Similarly here, remember B1, it's when the boundary of the Born region is less than or equal to 1/2, and this is when the boundary of the Born region is greater than or equal to 1/2. Now we have proposition 4.2, where we do the inverse, where k equals 1, only one quantizer in 0 to 0.5, and two or more quantizers in between 0.5 and 3/4. We have the expressions for that. And proposition 4.3 will consider the cases whenever we have more than two or more um, quantizers in the first interval and in the second interval. I'm referring first interval, second interval as follows. So um, from 0 to 0.5 is the first interval. From 0.5 to 3/4 is the second interval. That's where we are focusing on. Lemma 4.4. For any even positive integer n greater than or equal to 4, let alpha sub n be an optimal set of n means for p. Assume that the cardinality of the uh, quantizers, so the number of quantizers between 0 and 1/2 equals to k. And again, k depends on n. And the number of quantizers as in the interval 1/2 to 3/4 equals to m. So here we are going um, to define m as the quantizers between, and this is important, the open interval 1/2, 3/4. So 3/4 will no longer be considered. Um, like in for the value of fm. So for example, if um, well, I'm considering here even integers for n equals greater than or equal to 4. So we don't expect to have any quantizer at 3/4. So what this is basically saying is that for example, when n equals 4, if we go to the next even positive integer, 6, we expect to have another quantizer either in the first interval or the second interval. So consider the case when n equals 4. We have only one quantizer in the first interval. Remember, forget about these two. We're only focusing in this region right here. So there's only one quantizer in A1. There's only one quantizer between 0 and 1/2, and one quantizer between 1/2 and 3/4. So k equals 1, m equals 1. So in the next, if we consider the next even positive integer, n equals 6, what this lemma says is that the next quantizer could be either in this interval right here or in this interval. But it's not always the case that the next possible quantizer will appear in the first interval or the second one. And it's not always the case that, for example, the next one has to be here, to be 2, 2. Okay, so here we have k equals 1, m equals 1. Here we have k equals 2, m equals 1. So either k or m will have the same k or m from the positive integer from before, and the next one will be either in one of the and the other one will have the additional quantizer. Similarly for odd positive integers, we have the same pattern emerging. So when n equals 5, we have that it's one quantizer here, one quantizer. Remember, we are not going to consider this one for this lemma. We have one quantizer in this region. The next quantizer appears in this case here, but for n equals 9, for example, we don't know. We have to check what happens at n equals 9. But according to the lemma, it will be either in the first, the next quantizer will be in the first interval, and the other will stay the same, or in this interval, and we'll still have two quantizers here. So everything reduces to finding the value of k that gives the lowest distortion error for a given n. So remember, our goal is to find the quantizers for n greater than or equal to 5. And what we have discovered so far is that if we find the value of k, we can then use the propositions 4.1, 4.2, and 4.3 to find the lowest distortion error, depending on if, we have to consider the cases where the boundary of the border region is located, and we also have to consider if n is even or odd. So now to move with the algorithm, we're going to be defining a real value function, f of k and m, on the domain of the Cartesian product of the natural numbers. And we are not going to consider the point 1, 1, such that f of k and m equals to the minimum distortion error we defined before. So basically, we're going to define this function that finds the minimum distortion error of B1 or B2 that we defined earlier. B1 is when the boundary of the border region is less than 1/2. B2 is when the boundary of the border region is greater than or equal to 1/2. With the help of the following sequence, for any given n, we can get a possible value of k and then observe the pattern. So we're going to be defining this sequence when n equals 1, an is 0, and when n is greater than or equal to 2, it follows this. And we can observe here the first elements of the sequence. So this will be used to give or propose an initial guess for k. Okay, this sequence will give an initial guess for k, and then we're going to run an algorithm that's going to check that k is the actual value that our optimal set will have. So, for example, if say we are um, let's check, for example, let's suppose n equals 5. What does that mean? N equals 5 means we expect to have 5 quantizers, right? And we expect to have one quantizer at 3/4. So what will be the sequence? What will be the initial guess for k if n equals 5? So this is when n equals 1, 2, 3, 4, 5. Okay, the initial guess for n equals 5 is that the k, remember what is k? K is the number of quantizers between 0 and 0.5. So here this means that we expect to see, or the initial guess for k is that we're going to have one quantizer between 0 and 0.5. I don't know if I have here. So the initial guess of 1, it's in this case correct. Okay, we only have actually one quantizer between 0 and 0.5. Look at here. When n equals 7, we have how many? Two quantizers between 0 and 0.5. N equals 7. So let's see the number here that the initial guess from the sequence will give us. So 1, 2, 3, 4, 5, 6, 7. Okay, the initial guess for k is 2, which in fact is correct. But let's not get confused that this is going to give us the actual value of k. We're going to have to run an algorithm to check if this is true or not. By remark 4.8, let m be greater than or equal to 5. K and m will be positive integers, and m will be defined as the floor function of n divided by 2 minus k. So remember, if we know k, we can calculate m due to the symmetry. Not due to the symmetry, sorry. If we know k, we can calculate m as follows, and we later on can calculate the remaining quantizers. Okay, so when n equals greater than or equal to 5, and then as before, the number of elements in the interval 0 to 1/2 equals k, number of elements between this interval equals m. Thus, for a given n greater than or equal to 5, if we know the exact values of k and m, then by proposition 4.1 through 4.3, we can easily determine the optimal set alphas of n and the corresponding quantization error. Meaning what? Meaning that for any n greater than or equal to 5, if we know k, we can get m by this formula, and we can go to propositions 4.1, 4.2, or 4.3 and calculate the optimal set, the remaining quantizers, and the corresponding quantization error. So key, again, this I have made this pronunciation mistake over and over again. K is the key for finding the optimal set of n means for any n greater than or equal to 5. K is the key, is the important piece. So let me explain how the algorithm will work. So let's suppose we want to find the quantizers for 7 means when n equals 7. Okay, the algorithm is that for in that case, any n greater than or equal to 5, and using the function defined before in 4.6 and the sequence defined in definition 4.7, the algorithm will run as follows. K, we're going to assign K the the initial guess that I mentioned you about the sequence, like the number of that the sequence will give initially, and we're going to assign that to the variable K. And we're going to calculate, um, remember, the minimum distortion error with that K. With that value of K, we're going to, remember, find the minimum distortion error B1, B2, and those will, again, have to be calculated depending on, like B1, it's calculated when, or considering the case when the boundary of the border region is less than one half, and this B2 is when it's greater than or equal to one half. So what F is going to give us is the minimum of those distortion error. Okay. So after finding the minimum of the distortion errors, we will go into the sequence and now calculate the value for k minus 1. So in that sequence, we're going to move uh, to the k minus 1 number in the sequence and calculate again the minimum distortion error. And if the new distortion error when k minus 1, when we're considering k minus 1 is less than the previous distortion error from the original, from the very first distortion error we found, if it's less than the previous one, we're going to replace k by k minus 1. And now k minus 1 will be our k, right? And if not, um, if it happens to be that the very first guess of k is less, the distortion error is less than when we consider the element before in the sequence, then we're going to compare it with the element after in the sequence and check again. Is the distortion error greater or less? Um, and that's basically it. If the original one was less than the k plus 1 element in the sequence, then that means that our original guess was correct, and k is that number. So we found the number of quantizers in the first segment. We can find m, the number of quantizers in the second segment, and then we can find the rest by symmetry. So this is basically, and here some examples of different values of n. So whenever we try n equals 5, then the sequence told us that k was 1, and then when we put that 1 into the k here, by the algorithm at the end, at the very end, k equals 1. That's the actual k, and meaning that the optimal set alphas of 5 means contains one element from the interval 0 to 1 half. So if k equals 1, we only have one quantizer in the first, from 0 to 1 half in the first segment, first interval, which is clearly true by proposition 3.5. If n equals 6, then the sequence tells us that k equals 2, and when we run the algorithm, at the end we get k equals 2, which is true by proposition 3.7. When we try n equals 5, when n equals 50, then k equals 15, meaning 15 quantizers between 0 and 1 half. When we run the algorithm, we obtain the same answer. When we tried n equals 1001, the original k by the sequence told us that k was 304. And when we run the algorithm, we obtain that k, in fact, is 307. So this is one of the examples where the algorithm actually gave us the actual k. Okay, when it was comparing with different values of k. Thus, we see that with the help of the sequence and the algorithm, we can easily determine the exact values of k and m for any given integers n greater than or equal to 5. Hence, as mentioned in remark 4.8, we can obtain the optimal set of n means and the corresponding quantization error for all positive n integers n greater than or equal to 5. These are my references, and thank you very much.